Yep, all great things to try at one point or another. Today we're going to continue with lists and list-based data structures. I will mention that on Thursday we're going to have to cut it short, probably only 45 minutes because I've got to skedaddle over to the event center for a second COVID shot, and they will not accept reappointments on that. So when you're able to, oh no, we're good. When you're able to, get your shot as soon as you can. Don't pass up that opportunity. But anyway, remember that we are live on Piazza. We've got good on the stream here today. Last time we looked at array-based lists, where we created a list, and then inside the way that we actually stored things was using an array, which is nice because an array stores everything contiguously. Here's the first element, right next to it in memory is the next element, right next to it is the next element, etc. It's all contiguously stored. And that means that you can use random access. That if you want the 10th element, it's just start at this memory location, compute an offset to the 10th element, and you can jump to that memory location pretty easily, right? That's all done by the language itself anyway. But the challenges were to get it to grow dynamically in size or shrink. We didn't do that part, but doing everything in terms of the underlying array. One alternative to that is linked lists. A linked list is a little bit different in that each element is stored in a node, right? So a node is simply just this thing that holds an element, but it also holds a reference to another node, right? Each node contains an element and a reference to the next node so that we can link them all together. Here's a visualization of that. We do have some additional terminology to understand here. At the head of the list, we call that thing the head, right? At the end of the list, we don't call it the end of the list, or like the head of the line, the end of the line. It's more like an animal, the head of the animal and then the tail of the animal, or a snake or something like that. It's nice to visualize it as a snake if you want to use the head and the tail kind of idea. So this is the first element. Then that element has 42 and 49, and then it also has a reference to the next element. That has a reference to the next element, has a reference to the next element, until you get down to the last element, which is the tail, the end of the list. And then there is no, or for all intents and purposes, there's no reference to the next element because there is no next element. So that's what it looks like visually, right? How might we do basic operations like put stuff in, take stuff out, retrieve stuff, etc.? Well, there are a couple of ways that you can visualize this. For example, if we wanted to insert at the beginning of this linked list, what would it look like? Let's go back to the array-based list. If I've got an array with 4 elements here, and I want to insert something at the beginning, what do I need to do first? I need to shove stuff down to make room for it. I need to shift everything over because everything is stored contiguously. With the linked list, I don't have to worry about that. If I want to put it at the beginning of the list, what do? I create a brand new node and then make it point to the head. So let's look and see what that looks like. Let me go ahead and insert 42. All right. That creates so that went kind of quick. That's all right. I can go ahead and rewind here. All we have to do is create a new node, put 42 into it. 42 then will reference the old head, and this is like a chain, right? And all we need to do is take visually, we just need to take both ends of the chain, pull it taut, and it looks like a brand new list, right? With 42 now at the beginning. What if we wanted to insert something at the end? So let's insert something at the tail. We'll go ahead and insert 101. Actually, no, we can't go that high. Let's go ahead and go with 99. Right? Right. So the first thing, what we did was we just took the old tail, created a new node, and made the old tail point to the new tail. Right? What does it look like if we insert something in the middle? So it's still index-based. That is, the first element is at index 0, even though we're not jumping to an index like we would with an array. But this one is associated with 0, 1, 2, 3, 4, 5. So let's go ahead and insert something here at index 0, 1, 2. I want to insert something between 49 and 8. So let's insert and specify both here at 0, 1, 2. Okay, and we'll go ahead and insert, I don't know, give me your favorite number. 3? All right. Let's make it high so that we don't mix it up with indices. 33? All right. So again, just pause. Let me go reverse. Now, what do we have to do in order to get there? Well, with an array-based list, we could immediately jump to that index, shove everything down to make room for it, and put it right there. Here, we actually have to start at the head of the list and traverse next, until we find the element that we're looking for. At that point, because I've found 49 and 8, I need to insert between them. So I create a new node here, make that point to 8, make 49 point to 33, the node containing 33, and then again, pull the chain taut. And it's been inserted. So there are a couple of steps here first you have to find where you want it to go. Then you need to create a new node, and you need, just yank this chain apart, tear it apart, put it in the middle, and put it all back together again. Yeah?
Is there any sort of sort function for them?
Not like a list is ordered, but it's not necessarily sorted. Right? You're talking about a different type of list, a sorted list. Right? Or a sorted set, or whatever, however you want to think about it. In which case, you could use the same principles, a linked list or an array-based list or something completely different, and then you could impose an ordering on it. But you want to insert this element? Okay, it doesn't belong here, it doesn't belong here. Oh, that's where it belongs because it's between these two in the ordering, right? So a list is ordered. There's a first element, there's a last element, there's a fifth element, right? But it's not necessarily sorted. So that's a different type of list, a sorted list. That's what your last assignment is, to design one of those. Okay? All right. So now that we have a visualization of this, what I want to do is I want to implement it using Java. Right? Now, I've immediately started out here by learning from my mistake last time, where our initial design for a list, for an array-based list, remember that we had an array of integers. And then we realized at the end that once we had everything working, this is only good for integers. What about doubles? What about strings? What about something else? And then we came back and we parameterized it and realized that we only had to change a few things here and there. Otherwise, all the code was still the same. I'm going to start out that way. I'm going to start out with a parameterized class here, okay? Now, I need to design the state of this list. So, what are we going to keep track of? Are we going to keep track of every single one of these nodes? If I did, what would that look like? It would look like an array. And, well, if you're shopping for an array-based list, go there, right? Here, we need to make a linked list, where we don't keep track of all the elements. We only keep track of the head element or the tail element, right? And or, if you only keep track of the tail element, that's kind of weird. Just go ahead and flip everything around, right? What we're going to do is we're going to keep track of just the head element. You can keep track of both, all right? And you can even keep track of some subset, in which case you've got a special linked list called a skip list. Read the book if you want to take a look at what that looks like. Anyway, we're only going to keep track of the head here. So let me come over here. Private head. What's its type, though? Is it an integer because we're storing integers? Nope. Is it an element of type T because we're storing elements of type T? Kind of, yeah, that's part of it. Right? If you look at one single node here, let me go ahead and create random fixed size. Let me create a list of size 1, randomized. What does that look like? It's just a node. It doesn't have, it has a reference to the next node, it's just that it's pointing to nothing, right? Imagine like a dotted arrow coming out of this and it's not pointing to anything. So not only does a node have a reference to the element that's stored inside the node, it also has a reference to something else. So we've got 2 things here for each node. What is that screaming out to you? Multiple pieces of data that should be grouped together because they form one entity. Make a class, exactly. And yeah, I'll go ahead and start from scratch here. You can see that I already did this, but that's okay. And I'm going to also parameterize that node class because that node holds something. It doesn't just hold integers, it doesn't just hold strings, it holds something. It holds something of type T. So 2 things, private final element of type T element, and private something next. Right? So why did I make, I'm making this final because once you create a node and you put something in it, I don't want that to be changed. Right? You prefer immutable objects. I'm not going to make this one final. I could redesign it, have a copy constructor or whatever. But ultimately what I'm going to do is when I insert something in the middle of a chain of elements, I do want to change what this is referring to. This element is referring to this next node over here. I want to change it so that it's referring to this new node down here so that I can put something in the middle of the chain. So for at least for an initial design, I'm going to make it so that that is mutable, that you can change what the next element is pointing to. Don't make it point over there anymore. Make it point over that way. Right? What is its type, though? Is it just an element? Nope. What is it? A node. Right? Another node. Right? So the next is a node that contains an element. And also a reference to the next node, next node, next node, next node, etc. Right? Don't think of this as a recursive definition either. Yes, this class owns an instance of itself, but it doesn't own itself. Right? If I said next is equal to this, oh, will that even compile? Oh, it will. Now it is completely self-referential. Don't do that. Right. Actually, I'm gonna leave it like that for a second because I'm not so sure that that actually is compiling, or if it's just not realizing that that's an error because it won't compile because of this thing. So let me make sure that we're actually setting this element here. I'll go ahead and create a default constructor, not a default constructor, but a constructor that takes an element of type T and assigns it. This dot element is equal to element. Right. Oh, and it is. It is compiling. Don't do that though. Weird, bad. Now, what about this dot next? If I just create a node and I put this thing in it, 22, 42, whatever, what is it referring to as its next by default? What do you want it to refer to? I don't know. So I don't know is, in Java speak, would be null. Okay, that's reasonable. I'm not going to put this line of code here because that's what the default value is anyway. That member variables here that are not assigned, they get a default value null if they're object references. If they were integers, small I integers, they would end up getting a 0, doubles 0, Booleans would get a default value of false, etc. Right? Okay. What else do you want in a node class? Right now, we're just designing this node. We're not designing the list yet. That list is over here, right? And we're not done yet. So what else would you find useful in a node class? If you put something in the node, you certainly want to retrieve it, right? So maybe a getter. If I've got the one node, maybe I want the next node. So another getter. If I've got one node and I want to set its next node, probably a setter because that's why I didn't make it final, right? All right, source, generate getters and setters, select everything, done. Good. Yeah.
Would you want another, what's it called, constructor that would include both the, like the...
You could you could have another constructor that took both of them. That I've got the element and I've got your next node right here. Here you go. You take care of it. If we need it later on, we'll go ahead and add it. But for now, I don't need it. You ain't gonna need it, and then Yagni, but add a Y to that. You ain't gonna need it yet. Okay, we might need it later. Keep that in the back of your mind. Right? What else? Anything? So if I'm going to be traversing nodes, next, give me the next one because I'm going, let me regenerate this, some random, all right, there we go. And if I wanted to search, say, for 89, what would that look like? I would start at the start of the list, at the head of the list. Traverse next, that's not what I'm looking for. I'm looking for 89. 6 is not equal to 89. Next, that ain't it. Next, that ain't it. Next, hey, I found what I'm looking for. Done, right? So I'm going to be doing a lot of traversals here. One thing that might be useful is I'm on a node right now. I'm on, say, node 41. I want to know if I'm at the end of the list or not. Should I proceed? Or am I going to walk off the face of the earth, right? Flat earthers. So what would be helpful maybe over here in this node class? Is last node, from the node of the perspective of the node, it doesn't know where it is, right? It only knows its nearest neighbors, right? But one way that you can determine, do I have a next, would be has next. Next, right? Some sort of a method like that. Was that what would be your suggestion? Okay. So has next, that sounds like what kind of return type there? Boolean, right? True or false. If some condition, return true. Else, return false. So when do you have a next value? When next is not null. So if next, this dot next is not equal to null, return true. Otherwise, return false. If else, return true. If this evaluates to true, what will I end up returning? True. If this evaluates to false, what will I end up returning? False. So if x evaluates to x, why don't I just return x? Let's simplify this code. Return that. Right? And because I like it so much, this is the best. This is the best way of handling it. If we need more stuff, we'll come back. I mean, it's iterative design, right? Like, oh wow, it would be really nice if I had a method that did this for my node class. All right, well we can come back and implement it. Right? Yeah.
Should we have some kind of comparator? Just like if you're going to search for an element.
That's a good question. Where would the comparator belong though? Like we did last week. Would it belong in a node? I'm a single node. I'm comparing myself to, I'm just me. I live in a world that I've got my element and I've got a next. I suppose I could always compare my next neighbor's element, but that's not as useful as say a list owning that thing. Right? So let's go ahead and continue with the list implementation here. Now the head is no longer an integer, it's not a t, it is a node containing an element of type t. Right? If you wanted to do extend this functionality to include a tail. Right? For example, private node t tail. Right? If you want to keep track of both ends. Now, should we keep track of every single thing? No, if you wanted to keep track of every single thing, you're shopping for an array-based list. Right? Go shop somewhere else. Maybe we want some other stuff. Well, again, we'll come back as we iteratively develop this thing. Let's create a constructor so we can actually use it. Public my linked list. Oh, let me No questions so far. Remember, we are on Piazza. Head is equal to this dot head equals. Now, if we're going to create an empty list, how would we do that? Visually, what would we end up creating? Create an empty list. Do you see a node there? Nope. So the head is referring to nothing. Nothing in the context of programming languages is null. And again, that's not necessary because that's the default. But I'm going to be making changes here later on, so I'm going to keep this for this version. Okay. Okay. What else? What do you want in your list now? Yeah.
More than one node.
Okay, more than one node. So I'm going to be chaining them together, right? I'm going to be linking them together. How do you get more than one node in there? In fact, there's 0 nodes in here. How do you get that first node in there? You need some sort of add method. Remember, this is a bag, right? It's a collection data structure. We need a way to put stuff in, retrieve stuff, maybe delete stuff, maybe update stuff, right? Just like we did with our list last week, our array-based list. What did we have here? Well, we had support for a comparator. We'll come back to that. What about increased capacity? Do we need to do that here with a linked list? No, why? There's no array, right? What this did was it created a new array that was bigger, right? There's no capacity constraint at all because if you want to add a new node, just create a new node and link it in somehow, right? It's not being stored contiguously in memory. One node could be way over there in memory. Another node could be way over there in memory. It doesn't matter because you're jumping around memory locations all over the place. You don't need random access. What about get element at index? Well, I want to start with something simple. What about add to start? Okay. What does that look like? Well, let's visualize it. Initially, we've got an empty list, right? Let's go ahead and insert add to start. That's the head of the list, 42. What did it do? It created a new node and made sure that the head is pointing to that new node. That's if the list is empty, right? So let's take that case. If this list is empty, right? Not real Java code, we'll come back and fix that, right? But it's helpful sometimes to design stuff by writing out in plain English, then coming back and filling in the blanks, right? That's the ideal programming language, natural languages, right? But we're not at Star Trek level yet. So computer, do this for me exactly, right? We can't even get Alexa to understand, basic stuff, right? Exactly, we can't get people to speak. Good job. All right. So if this list is empty, what did it look like? I created a new node, so let's create a new node. Node t new head, right, is equal to new node. And what are you putting in it? You're putting x, right? You're given x and you want to add x to the head of the list. Okay? Now, if the list is empty, there's no other node to work with, so all we're doing is making this list's head point to the new head. That's what it did over here. Now, let's suppose that there's 50 things in the list, whatever. Let me create a brand new randomly sized array. That's too small. Create something larger. There we go. All right. So suppose that this is the list right now. It's not empty. We need to insert at the head, and I'll use 42 again here. All right. And stop, pause, go back. There we go. So the first step is, again, create a new node. I've got code to do that. Next step. Make it point to the old head. Right? The new head, make its next point to the old head. So new head dot set next to this current head of the list. Then what? Make head point to this new node, because otherwise head is pointing into the middle of the list somewhere, right? So this dot head is equal to the new head. And then, just for visualization purposes, pull your chain tight. And you get that. Right? Questions?
Well, I was gonna say, the thing you link it to isn't the node itself, it's the element in the node.
I put the element in the node, and now it's a node. So, and a node has next or previous if you it's doubly linked, but we're not doing that.
So is head just like a,
There's only one head, the list's head. That can change as you're adding stuff to the beginning of the list, but there's only one head. Right? Let me go ahead and reverse this a little bit. Before we set that head, the head was still referring to now the second object. Right? Only when we change the list's reference to the head to the new element here do we get a list where 42 is now the first element.
so
Pulling it tight looks like this.
you're not deleting the old head.
Nope.
You're just
I never deleted the old head at all, right? I just made the old head be referenced by the new head, and then this head is now pointing to the new head. So tell me, how do you determine something is empty? How did we create an empty list? If the head is null, if this dot head is null, then I know that it's empty, and in which case I need to create a brand new head. Right? That seems kind of useful. And it also, in its current form, it's not at all English, Englishy, right? If that's a word. What if we were put this into a method that had a more descriptive name? Public, Boolean, true or false. Is it empty? Return. Well, it's empty if the head is null. It's not empty if the head is not null. So just return that. And now we can use more appropriate Englishy kind of question. If this list is empty, right, then do this thing. Otherwise, do this thing. Okay? In the interest of improving this code, do you see a difference between this code block and this code block? Only one line. What if we were to do the same thing up here? Is that going to screw anything up? New head set next to this head. If this head if it's empty, then this head is null, so this is equivalent to doing this. But that was already the default. Right? It's not pointing to anything at all. It's pointing to null. So there really is no difference in these two cases, at least for this operation. And if you can get by with collapsing a code that covers more cases, you do it. In fact, this covers all the cases. Right? Both cases. There's only two. Let's actually test this. So I've got a my linked list. And I'll just go ahead and do integers for simplicity. L equals new my linked list. Help me out here. What should I put in? For int I'll go by tens again. I is equal to 10. I is less than or equal to 100. I plus plus. I will go ahead and add to start I. Now I'm going 10, 20, 30, 40, but I'm always adding it to the start. So what should it look like at the end? 190 reverse 190, 80, all the way down to 10. Yeah.
Unless your I is only increasing by 1 each time.
Oh, thank you. I did say by tens, didn't I? There we go. Otherwise, it would be 10, 11, 12. It'd be a hell of a lot more than I want in there right now. And I'm not going to print I, I'm going to print L. All right, crossing my fingers here to see if it works. And it did. It's just that it's not very useful, right? The default behavior of the toString method in any class is going to be the fully qualified package class name along with a cryptic Java virtual machine memory address. that's probably going to be the same every single time because it's relative to the JVM, which might be loaded up at different memory locations as far as the computer is concerned. But with respect to the JVM, it's always some deterministic memory address. That's not too helpful. So let's create a public string to string method. Oops, there we go. Now, how do we go about designing this? I want it to look like that. 42, comma, or we could put in an arrow. That'd be cool, right? 42, arrow is 26, arrow, 9, dot, 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 right? I want it to print from the first one all the way to the last one. So, what do I need to do? I need to start at the head. There's a concept of a current node. This is the current node. Print it, or concatenate it to some string or something like that. Then I need to go to the next node. Print it. Go to the next node. Go to the next node. Print, 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 print each time I do this. But once I get to the tail, print it or append it, whatever. Go to the next node, and I stop because that's the end of the list. Right? So let's come back over here and do that. I'm going to create a string builder. And ultimately, that's what I'm going to return as a string, though. Dump it to an immutable string. I have this concept of the current node that starts at the head and goes all the way to the end of the list. So I need a variable to hold that idea. Right? A node called current. Now, what should I start that out as? The head. The only thing I can, because the only variable in this class is head. And best practice dictates that I should always use the this keyword, even if it's not necessary. All right, current. Now, what kind of a loop do you want to use here? A while loop. Why did you jump to a while loop? While the current node is not null, process it, right? So while the current node is not null, well, current node is not null, not equals null, append it. So sb.append. Now I'm not going to append the node, I'm going to append the element in the node. So current dot get element. And then I can go ahead and concatenate that with a cool looking arrow here. Okay.
You only want to concatenate with the cool looking arrow if it's not the last element.
Okay, we are gonna, or if it's commas, we will have a trailing comma here, just like we did last time with the array-based list. You'd have to change your logic here a little bit, right? So, yes, that we're gonna have a trailing arrow that goes off to nothing. I'll leave it to you to solve that problem. Right? But we're not done yet. I append it. I need to set myself up for the next iteration. I need to advance this current reference to the next node. Current is equal to current dot get next. Let's see what that looks like, what that produces over here in the demo, sorry. Hey, 100, 90, 80. I'm not liking those arrows now. But we'll go ahead, that's fine. We can go ahead and change it to a comma. That looks more like a list to me. Right. Now, if you wanted to leave off that trailing comma, what would you do? You'd have to stop one iteration short, which means that you'd have to ask, while the current's next is not null or something like that. You'd have to look ahead a little bit farther to see, am I about to fall off the list, right? Okay, that looks good so far. Right? Questions so far? No? Okay. All right. That looks good to me. What else did we have that we might want? Ooh, how about get size? Suggestions. Public int get size. How about We cut, paste. But we're not building a string anymore. We're not appending anything. We have int size is equal to 0. And then while you're traversing, I plus, or size plus plus, and then return size. That sounds reasonable at first, right? Because that's what we just did down here. Let's go ahead and try it and see if it actually works in our demo here. System.out.println l.size. What would you expect here? 10, right? There are 10 elements in there? Oops.
It's not printing out everything because it's stuck in
Oh, good. What did I erase accidentally? I just increment the size. What am I doing? I actually need to make progress towards the end of the list. There we go. Now that should be 10. All right. So, seems reasonable at first. If I do this a lot, though, what do I end up having to do? If there are a billion elements in my linked list, I have to end up counting a billion, 1, 2, 3, 4, all billion of them. Is there a better way? I could probably keep track of that, right? If I put something in, add 1. If I take something out, subtract 1. Right? I don't have to recompute this every single time if I keep track of the size. Private. It's not going to be final, but it's going to be int size. What should its default value be? 0. Right? You start off with an empty list. What's its size? 0. You do have to be careful, though, because if you're going to add to the start, what should you do there? There we go. Get size now. You don't need to recompute it. You just need to return this dot size. And now we can go back, actually, if you really wanted to, and change this while loop into a more idiomatic for loop if you wanted to, right? There are 10 elements in there. Just execute this loop 10 times. Right? But I'm going to leave it as it is. Right? Okay? What else in our array-based one? Add to start, add to end. Okay, or add anywhere. Okay. Let's come back over here and implement that. I'm going to keep the same error checking that I had before, but all this stuff is now, who cares, right? Because it's not an array anymore. What's the first step? Add element at index. Let's visualize this again here. So I'm going to insert an element at, say, 0, 1, 2, 3. I'm going to insert something between 9 and 49. So, this one. 3, I'll insert, give me your favorite 2-digit number. 25, all right. Go. Pause. What does it have to do? It has to start at the head, increment, 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 until it finds the location that you wanted it to, where you wanted it to be. Note here that it's keeping track of a previous and a current. They called it after, but let's call it current in our code. The current node and the previous node. So that once you've found both of those, you're going to insert it between those two. To make room for it, you're not even really making room for it because you don't have to shift anything down, right? All you're doing is creating a brand new node, making the previous point to it, or making it point to the next, and then making the previous point to it, and pulling that chain taut. Right? So, step 1. Is it what? Iterate. Find the location you are looking for. ... Before we do that, is there a corner case that we might want to consider? That was this visualization. What if I gave you a empty list and then insert 42? Well, here, insert 42 at index 0. That would be the only valid one. Otherwise, we'll throw that exception. What does that look like? Oh, between 1 and 1. Okay, fine. Oh, sorry. I guess it's the other way around. Okay, fine. 1. All right. Head. 42. I don't know why it's not letting me do that, but there you go. That's what it would look like if you wanted to insert it at index 0 on an empty list. Should we take care of that corner case? At least initially, let's do that. If this dot is empty, if this is an empty list, it doesn't matter where you're inserting it, because if it's an empty list and you gave me an index other than 0, we would have thrown this exception at you. Right? So we know that we're okay at this point, that it's empty, and you wanted to insert it, well, the only place that you can insert it by creating a new node. Add to start x. Else. Now we know that the list is not empty. So we do know that we have to traverse to the place that we're looking for. Right? So traverse to the ith node. I'm going to take and steal this code right here. I'm going to have a current, but instead of a while loop, I know exactly how many steps I want to go. If index is 5, I want to go 1, 2, 3, 4, 5, because that's where it needs to be. So a for loop for int I equals 0, I is less than index I plus plus. And I don't care what's in there. I'm not appending anything. I'm not looking at it. I'm just go to the next one, go to the next one, go to the next one. So current is equal to current dot get next. At that point, I'm where it wants to be. So I'm at, let me create another random list here. 0, 1, 2. I want to insert it right here. So what I'm going to have to do is I'm going to have to create a new node, make it point to this old node, but then the previous node has to point to this new one. Right? So again, let's insert at 2. We'll insert 42. Go. Pause. Once we're there, this is my current node. Create a new node. So create a new node. Right? Node t, I'll get your question in a second here. New node is equal to new node. I can't get too creative here. You could call this, sometimes in graph theory we use u, v, or x and y or something like that. New node, whatever, right? And we'll put x into it. At this point, I'm here. Next step is make it point to the current node. So the new node dot set current to the current node, or set next to the current. Right? And we're at this point. The next step, however, will be making the previous node point to me, or point to the new node. Do I have a previous here? Nope. Fine. What should I have done? I like that. You're jumping to the better solution already. My initial solution was going to be to keep track of both the current and the previous, right? And then move along current, previous, move them both along, right? You realize that we don't have to keep track of both. If we just stop short one, then we can always get the next one. So current, stop short, and then node t previous is equal to, or sorry, this will end up being previous, current equals previous dot get next. Right? Now I've got both current and previous. Created the new node, set the new nodes next to the current, and then set the previous dot set next to the new node. Okay, what?
If the index is 1, I is equal to 0, I is not less than 0, so it'll just never go.
There might be an issue there on a corner case where we're adding something to the head of the list. Good thing we took care of that. Right? Good insight though, right? And we'll definitely want to test that. Right? That's why I handled that corner case to begin with, though. Right? And I would have, we would have gotten there. We would have come back around to that. Right? All right. Question online: if index equals 0, then add to beginning would be better than check if the list is empty. Oh, okay. Never mind. Checking the list is empty would be better. Yeah. Actually, is empty. You could I think the reference here was you could also refactor this now that we're keeping track of the size. It's empty if this dot size is 0. Right. Same. 6 of one, half a dozen of the other, whichever one you want. Right. Okay. What do I need to make sure that I take care of now that I've successfully added the node, though? This dot size plus plus. There we go. Okay. Let's test this out in our demo here. Let's add 42 to index 0, 1, 2, 3. So it's going to end up being 190, 80, 42. So L dot add element at index, what did I say? 0, 1, 2, 3. Add 3 index element here. There we go. And then print it out again so that we actually let's print both of those things out to make sure that we incremented the size correctly to 11, and looks good to me so far. Right? What other corner cases should we take care of here? Your case of what happens when we do this at 0. Right? Oh, okay. So we inserted at 1. That looks correct. 0, 1, right? That's where we inserted it. What happens when we insert at 0, though? It didn't work. No, it's definitely not. Here, I'll clear it out just to make absolutely sure. That doesn't sound right. So let's go ahead and set a debugger. Start this up. All right. Step into that, and then we'll have to ignore all this stuff. That's internal. No. Start it over again. Start it over again. There we go. Step into, step over. There we go. Now step into. Okay. So we've got X, which is 42. We're going to insert 42. We're going to insert it at index 0. Let's trace this through and find out what's wrong. It doesn't throw an exception, so I'm going to go ahead and go over that. It's not empty, is it? Nope. In fact, you can hover over these things. Maybe no longer, but it's definitely not empty. All right, there. Is empty return false. You can see it up here. It's really tiny if you can't see it, but it did return false. Okay, so previous is equal to the head. Okay. And I can actually look at previous and see that, I don't have a toString method here, but if I expand it out, I can examine that its element is 100. And that jives with what we've got down here. Okay. All right, so step, what happened? Like you said, index minus 1 ends up being, we never called next. So previous is still at the head, right? Now current is going to end up being what? This is head and this is previous, but the next is now 90. So let's step over. And you see, here, I'll expand that out. You see that the element is 90. So do you want to insert it right here between 100 and 90? That's not what the meaning, right? That's not what our intention was. But that's why it's happening here, because we took this shortcut. All right, so let's rethink that shortcut. Go back to the Java perspective here. All right. What did we have it at before? That this was current. Current is equal to current, and I am 99% sure that that'll work. That'll get us to the ith element, but we no longer have a previous. Okay. This really is only a problem if we're inserting at the beginning of the list, right? Any other index, 1, 2, 3, all the way to the end, that seems like it would be taken care of to me. What's another corner case that we could think of? If it's empty, we insert it at the start. If you want to insert it at index 0, another way of saying that is you want to insert it at the start. So let's take both of those cases, those corner cases, or dot size, get size. If it's 0, then both of those we would insert it at the front. And now we can revert back to your solution of stopping short and then getting the next, right? Okay. I want to improve this a little bit more, right? Let's see. Let me go ahead and get rid of this stuff. I mean, it takes two cases where you would want to insert it at index 0, and it takes care of both of those. Inserting into an empty list will insert at the head. Inserting into a list at index 0 is also inserting at the head. And it takes care of both of those by calling just add to start. Right? Oh, right. What these you mean? Oh, sorry. Oh, that's what you mean. Okay, sorry. This dot is empty, or index is equal to 0. There we go. But if it's empty, then the only valid index is 0. Otherwise, we'd throw the exception at you. So we actually don't need this first part either. Right? I like that better. Right? So if you're inserting at index 0, then we'll just call this over here. All right, now I lost my code there. I want to get the node at index I. ... You know what? That seems like such a useful piece of functionality. Maybe I shouldn't just do it here. Maybe I should put it into a method. Public node t get in node at index. Index. Right. And now we can repeat the code from before, right? First of all, we can do an index check here. If it's greater than or equal to size, because if there are 5 elements in there, you can't ask for index 5. It goes 0, 1, 2, 3, 4. Right? So we'll throw an index out of bounds exception for any of those. And then for int I equals 0, I is less than index I plus plus. Current is equal to current dot get next. Unfortunately, I've got to create that. So node t current is equal to this dot head. And then finally, return current. Right. And now I can use this down here with the same idea of stopping short, because we can always get the next, right? Actually, I don't even, get node at index. So, node t current is equal to, previous is what we want first. At index minus 1, and then node t current is equal to get node at index. Do I need to call it twice though? What does your trick look like in the context of this now method that I just made? Previous dot get next. I like that better. If there are a million elements in there, do you go over it once and then twice again just to get with the one right next to it? Or do you go over it 999,999 times and then just one more operation? I like that. All right. That looks like it works. Let's go ahead and we have to actually try it though. Add element at index 0. That works now. Add an element at index 1, so it'd be 142, et cetera, 2. This is just ad hoc testing. If you're actually testing this, you should automate it. You should test all the corner cases. Another corner case here would be adding it at the end, right? That works. Adding it at the end plus 1 should result in a exception. There's a problem here though. Let me go ahead and revert that to 0. What can I now do? L dot get node at index 4. Does that look like it's something that should be allowed? Over here in our array-based list, did I ever give you access to the underlying list or the underlying array? No, that would be a leaky abstraction. Leaking information out. Oh yeah, sure. Here you go. Here's the array. Screw it up however you want, right? Encapsulation is the protection of your data. It is the hiding of implementation details so that the outside world doesn't have to know. What the hell is a node, right? This is a list. I have no idea about nodes, right? So let's protect the outside, both the internal workings of the class as well as the outside world from a leaky abstraction. How? Making this private. Now I can use it down here just fine because it's private, but over here in the demo, you can't do that anymore. Much more sensible. Something that I would like to do though is L dot get element at index 4. And then I want to print it out. Can I do that? I haven't implemented it yet. What would it look like? Public T, because you're going to return the element. Get element at index, int index. What would it look like? It would look very much like get node at index, except instead of returning the node, you would return the element stored in that node. Well, if I've already got this, I can certainly get the element out of it. Nice. And now over here in this, it should be 4 should be what? 70? 0, 1, 2, 3, 4. 70. All right. What else would we have to implement to make this complete? Get element at index, add element at index, add to end. What would that look like? Yep. This dot, or not add to end. That's not what I wanted. Sorry. I've got too much stuff open here. Let's close this crap. All right. Add to, add to end is what I wanted, right? Yeah, there we go. Add to end. This dot, add element at index. You're going to add x, and what index do you want it at? This dot size. And you're done, right? Usually when you're designing, not even object-oriented programming, when you're designing methods, you design the most general method, right? You've solved all cases. Then more specific problems can be solved by calling some variation on that general method, right? So add element at index, that's the most general method. Now I'm thinking I want to go back and add to start. Well, I could just go ahead and call add element at index 0, right? No, why? Because it would just end up calling get start, which would end up calling the other one, which would end up ping-ponging back and forth. There's got to be a base case somewhere, right? Okay, I think we got everything, didn't we? Oh, index of, that's the last thing, right? Remember we went through this exercise where we had a comparator. If you did not provide a comparator at instantiation, we threw it back at you and said, you call them a name, right? Otherwise, we used that comparator and said, well, if the first one, is that the thing you're looking for? Is it equal to 0? Okay, yes, that's what you're looking for. Here you go. That's the index. Otherwise, next index, next index, next index. On an unsuccessful search, we return -1. What would this look like in the context of a linked list? Well, first of all, we've got to create that comparator, right? Let's bring that in. Got plenty of time to do this, right? And we also want a method that takes it. So I'm going to steal that code too. This comparator, there we go. And it's not going to be this, it's going to be this dot head is equal to null. Yeah, right? A lot of repeated code here. So I could have this more specific one that doesn't take anything, call this more general one that does take something. This null. Clean that code up a little bit. Right? What are you griping about? Certainly you're not complaining about the order. Oh,
No, the other one is called my list.
there we go.
That
Thank you.
one's called my list.
I only want that there. Now you should be happy. There we go. All right, now let me grab that code for index of. And help me out here. What should it look? Oh, I already copy pasted it here. What should it look like? Well, if the comparator's null, then we got to throw it back at them. Otherwise, we iterate through. We can't get the ith element here, but I can call t x is equal to this dot get element at index I, and then make the comparison here. This will work, but think about what's going on here. This goes back to the painter's paradox. If you probably don't remember, you might remember it once you hear it again. But you hired this painter, and you pay him by the hour. And the first couple of hours, you leave for a couple of hours, and you come back and check on his progress. Wow, he's done really well. He's painted a lot of the fence already. You come back another couple of hours, and he's only painted a little bit more. So you get, okay, maybe he's getting tired or something. By the end of the day, the fence is still not painted. He goes, all right, fine, come back tomorrow. Tomorrow he's even slower. He's only getting a few boards done at every hour or so, right? And so you finally say, all right, show me what you're doing here because it shouldn't be taking you this long. And the painter shows him what he's doing. He takes here's the beginning of the fence, here's the end of the fence. He goes to the beginning of the fence, dips his paintbrush, walks all the way over to where he's painting, continues painting, runs out of paint, walks all the way back to the beginning, gets more paint, comes all the way over here, more paint, back and forth. At the beginning, he was going fast. Why? Going back and forth a small distance, that's nothing. But once you've got to 100 feet and you're walking 100 feet back and forth just to paint one clapboard or whatever they're called, right? One picket, right? Then you're walking back and forth 100 feet at a time, right? Now, from the painter's perspective, he's doing really well because he's getting paid by the hour. What should the painter be doing, though? Take the damn bucket with you, right? We are not taking the bucket with us here. Every time we want to get the ith element, we start back at the beginning of the linked list, come to the ith element. You want the I plus 1th element. So the millionth element, we have to start at the beginning, traverse 1,000,000 times to get there. The 1,000,001th element, instead of using your trick and just get the next, get the next, get the next, we're going all the way back to the beginning, traversing all the way forward. It looks like good code until you understand the underlying data, right, or data representation of it. Let me show you. Go over here to the demo. It will work because this is a small list, only 10 things, right? You're only walking 10 inches back and forth, right? So int index is equal to L dot index of, what do we have in there? I'll go to all the way to the end, 10, okay? And system.out.println index. The index of 10 should be at the, 10? Oh, I didn't call the right constructor. Fine. Where's my demo from last week? There's my comparator. I want that comparator. bring it over to this demo. Oh, it is for strings. All right, that's all right. Integer, 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 integer. And I think we're okay. I have to change that one though, too. All good? What are you complaining about now? Oh, that's, I thought I copy pasted enough times. Compare, there we go. I erased that one. All right, sorry. All right, put that into my linked list. There we go. Now I called the right one, and in fact, I did get 10. Hopefully that's not confusing. We're searching for 10. It happened to be at 10. That's just a coincidence. Let's search for 42. That should be at index 0, right? Okay. Let's go and search for 10 again. But instead of having only 10 elements in there, let's go up by increments of 1, starting at 1, and go up to 1 million. There we go. All right. All right, sorry, stop. I don't want you to get the impression that it's slow because we're printing it out. So let me go ahead and get rid of all of this stuff. All right. And I'll print out a message here. Done inserting, ... Done inserting is going to end up being instantaneous. Okay? But that little red square there is telling you that the computer is continuing to go. Why? Again, the painter. He's not walking 10 inches anymore. He's doing a million iterations to get all, 500,000, it's doing 500,000 operations to get there. 500,001, it's doing 500,001 operations to get there. That adds up. In fact, this is on the order of 1 million times 1 million, and we call them quadrillions, right? 1 quadrillion operations, about that. 1 quadrillion divided by 2. Right? Should we wait? It will take literally hours or days to do this. Right? And again, if you're a computer getting paid by the nanosecond, okay, sure, yeah, I'll do that. But we're not. Right? We're paying for it. We're paying the fence painter. So we need a better solution. Here we go. Don't do this. Instead, do a traditional while loop here. Or it doesn't, I don't want you to get the impression that it's a difference between a for loop and a while loop. It's the operations themselves. What I'm going to do is I'm going to use a while loop similar to what we did down here. Right? So I'll start at the head. While I'm not null, instead of appending it, I will check to see if the comparator, if the key that you're looking for is equal to the current dot get element, then that's what you're looking for. I stop and I return I. Of course, I need to start I at 0 and increment it. I is equal to I, or plus plus, sorry. I'll just do it that way. And this is actually the first thing I should do. There. This sets me up for my next iteration. So I look at the current element. If that's equal to the key that you're searching for, output or return I and you're done. Now you can get rid of this. Otherwise, when you get to the end of the list, then there you go, -1. Now that thing that I told you would take hours upon hours upon hours, maybe days, is instantaneous. Nearly instantaneous. Right? That's the index of 10 at the very end of the list. Now, if you think this is basic, it is kind of basic, but it's the difference between a programmer and a computer scientist. I have seen actual production code using that the old kind of construct where they get element at index, and with no regard to what kind of list it was using, a linked list, an array-based list, etc. That you really need to understand what's going on under the hood in order to use things properly. And it's, when it's only when you get to code that this is not running, it's taking hours for this thing to run, or it's taking days, or being able to recognize when it won't execute within your lifetime or the lifetime of the universe, right? Those are the important things that separate a computer scientist from just a plain old programmer. Just remember the fence painter. All right, again, on Thursday we will be be cutting it short because I've got to go to a COVID shot. Again, get your shots when you're available or when you are able to.